Good afternoon, everybody, and welcome to another Geo-Institute live stream. We've got a great presentation for you today. It's the second of 3 live streamed Cross-USA lectures that we're doing in the summer of 2024 that we have christened the GI Summer of Live because of all the amazing live stream events that we have going on for you this summer. You can learn more about our other streams at our Eventbrite page. You can go back on the YouTube channel and watch the previous streams that we've done this summer. Maybe check out some of our pre-recorded content as well, including summer school. You don't want to miss that one. Those are all fantastic options for you to while away the hours. My name is Brad Keeler. I'm the director of the Geo-Institute, and as I said, we are thrilled to have you with us today for Kyle Rollins' second live-streamed Cross-USA lecture. A few things that we must say before we begin. If you are not familiar with the Geo-Institute, first, welcome. Second, after you watch this today, head over to geoinstitute.org so you can learn a little bit more about us. Some of those things that you will take in will be that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. If you like what you see today, and I think you will, you should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. One more announcement that we have to make before we're going here. Carl Terzaghi has come out of his case for the first time in quite a while to help me make an announcement that the second bobblehead in our series will be out this fall, and it will feature one Ralph Peck. You do not want to miss that. How do you get one, you may ask? Once we make the announcement that they're available, you make a $96 or more contribution to GI student programs. And as long as you're in the US or Canada, one of these will come to your mailbox. You'll also be able to pick them up at GI events all throughout the rest of 2024 and 2025. And of course, I am wearing my student competition t-shirt from Geo-Congress 2024 that helps to promote all the good work that our student programs help to fund. 100% of your donation goes to student programs, and 100% is tax deductible. Now, with that out of the way, we're very fortunate to have GeoPeer, our friends at GeoPeer, sponsor the Cross USA Lecture Series. For this, I believe, is the 3rd year in a row they've done it. We have a little message from them before we get on with the program. Thanks again to GeoPeer for their generous sponsorship of this lecture series, which began in 2010. And here to tell you a little bit more about that and to introduce today's speaker is member of the GI Board of Governors, our treasurer this year from the Georgia Institute of Technology. It is Susan Burns. Susan, welcome.
Thanks so much, Brad. It's really my pleasure to be here today to introduce the 23-24 Cross USA lecturer, Dr. Kyle Rollins. My name is Susan Burns, and I'm a professor at Georgia Tech, and I'm serving this year as the treasurer of the GI Board of Governors. I really enjoy this lecture series. It's a unique, almost very unusual combination of groups who sponsor this lecture series, including the Local Involvement Committee, the GI Board of Governors, and the Student Leadership Committee. Those folks come together and choose the lecturer every year, which gives us a very diverse and widespread appeal for the lecturers that you'll see in this series. The lecture started in 2010, and our recipients travel across the country, delivering lectures primarily to local chapters and to student groups, but some other groups as well, too. I also want to give a shout out to our 24-25 lecturer, Dr. Richard Bathurst, Professor Emeritus of Civil Engineering at the Royal Military College of Canada. And so with that, it's my great pleasure today to introduce the 23-24 Cross-USA lecturer, Dr. Kyle Rollins. Dr. Rollins is a professor of civil engineering at Brigham Young University in Utah. He has an extensive body of work, and his research expertise lies in liquefaction assessment, lateral resistance of piles and pile groups, passive resistance of bridge abutments, lightweight cellular concrete for retaining structures, as well as a range of soil improvement work as well. Dr. Rollins has a distinguished academic career with a long list of awards and extensive service to our profession. And so it's my pleasure today to welcome him to the 2024 Cross-USA lecture.
Thanks, Susan. Let's see if we can get this rolling here. Seen that all right? Okay, entire screen, click. Is it on there? Entire screen.
Bear with us just 1 second, folks.
Confidence is a preference for the habitual voyeur of what is known as. A morning suit can be avoided if you take a route straight through what is known as. John Scott Brewer's group, he gets intimidated.
Hello, everyone. Thanks for tuning in. Sorry for the little hiccup there. I'm excited to share some of our research with you today. And I want to express my appreciation to GeoPeer for sponsoring this lecture series. Today, we're going to be talking about the design for liquefaction-induced downdrag on piles. And we're going to use results from full-scale blast liquefaction tests to help us understand the problem. This research has been sponsored by the National Science Foundation, Caltrans in the US, Tonkin and Taylor in New Zealand, National Institute for Geophysics and Volcanology in Italy, Federal Highways, Transportation Research Board, and the Geofondazione, a pile driving contractor in Italy. Really appreciate their support. When we look at soft profiles that might have liquefiable layers, one approach is typically to use driven piles or drilled shafts. And then in that process, the applied load P here is carried by side friction, Q sub S, along the length of the pile, and tow resistance, Q sub B. If we plot the load in the pile versus depth here, we'll start out with a load of P at the top of the ground surface. And as we go down into the soil, we'll have a reduction of load in the pile as load is transferred to the soil by side friction. At the bottom of the pile, we'll have a tow resistance that has to be carried by the base of the pile. Now that tow resistance can only develop with a certain amount of settlement, and we can estimate the settlement that might take place with a QZ curve. That's the tow resistance versus the tow settlement. So when we first develop the load on the pile, this will be our settlement. If we have an earthquake event that causes shaking, the loose sand and medium sand might liquefy. And as that soil liquefies, the side resistance in that liquefied zone may go to close to 0, or maybe some small value residual strength. And that causes an increase in load to be transferred to the toe. And that increased load at the toe increases the settlement as well. Now, that's not all there is to it, because as the pore pressures dissipate and start to settle, we develop downdrag or negative friction or drag load in the top layer of soil, in this case, the soft clay. And that's not the only problem we might have, is because now that's going to cause some additional settlement to take place. Some people suggest using just a 0 value of negative friction in the liquefied zone. But if you think about it, the only way that the soil is going to really settle is if the excess pore pressures start to dissipate. And as they start to dissipate, effective stress goes up, and friction can develop on the side of the pile, which leads to downward force on the pile, or drag load. Now that process can lead to even additional settlement at the toe of the pile. So we need to take into account all these factors. From our testing in the field, and from at Brigham Young, and from centrifuge tests that's been done at UC Davis, there's good evidence to believe that we should design for something more than a 0 value in this liquefied zone. Now, we can identify the neutral plane here as the boundary between negative friction and positive friction. And that negative friction, or that neutral plane, also will give us a point, typically for simple problems like this, where the settlement of the soil is equal to the settlement of the pile. Now, can this ever cause problems? Is this just something for academics to worry about? In the Concepcion Chile earthquake in 2010, there was substantial damage due to liquefaction. And on Juan Pablo Seconda Bridge, there were sections where the piles settled 0.5 meter or more. And investigation suggests that negative friction was playing a role in this excessive settlement. At the Resurrection River Bridge in Seward, Alaska, during the 1964 Alaskan earthquake, liquefaction occurred even in these gravelly soils on the bridge abutments, and the settlement was great enough that the piles actually pulled out of the pile caps due to negative friction and drag loads. So it's a problem that we need to worry about. Our research objectives over the last 10 years or so have been to measure the development of negative skin friction during liquefaction and reconsolidation. We want to see what happens to the non-liquefied soils above the liquefied layer and in the liquefied sand. We want to see if the neutral plane concept can account for the pile settlement that we're expecting to see. We've also tried to investigate whether tapered piles can reduce negative friction in comparison with cylindrical piles, and investigated both liquefied and non-liquefied cases. And if we get time, we'll look at the behavior of pile groups where we think negative friction could be lower on the interior piles in the group, and investigate last if the original static capacity can redevelop after liquefaction has taken place, or if we need to account for that reduction going forward. So there's a number of methods we could use to investigate liquefaction and downdrag behavior. We could use laboratory scale testing like small centrifuge models. We could also use large laminar shear boxes like the one here in the at the University of Buffalo, where we've done some tests. The difficulty with this is that you have to try and recreate the soil microstructure. Might be difficult, and you've got sometimes scale effects to be concerned about. If you look at large-scale tests, maybe you could instrument a site in a highly seismic area. Hopefully, while your instrumentation is all working, an earthquake would strike and you'd learn something about what's going on. This is a long waiting game. Other alternatives would be used to use vibro-sized trucks like T-Rex at University of Texas, which can induce cyclic shearing, or use controlled blasting. Now, none of these methods are perfect. Each one has its limitations and advantages. So looking at everything we can get together, it adds another piece to the puzzle to help us understand what's really going on. When it comes to blast liquefaction, the advantages are that we can test at full scale. We can test the native soil in situ with the real microstructure and aging effects. We can liquefy large volumes at one time to investigate system performance rather than just a small element. And we can liquefy to significant depths, more than 15 meters. And another advantage is that we can produce settlements that are similar to earthquake-induced values, so that we are testing something that is a little more representative of what might happen in an earthquake. Limitations are that the mechanism of pressure generation is not identical to an earthquake, although shear strains are the predominant cause of pore pressure generation. We need to calibrate the earthquake conditions to earthquake conditions, and that's going to require some more research. And we have to avoid vibration disturbance to adjacent people and structures. Lastly, the full-scale testing is more expensive than small-scale tests. So when I first heard about blast liquefaction, my mind went back to a Western called Butch Cassidy and the Sundance Kid, where they're and this is the image that came to my mind. Butch was trying to use enough explosives to blow up the safe, get the money out.
Think using enough dynamite there, Butch?
So this is always a concern. We went to our first test site to do this in Treasure Island in San Francisco Bay. We were testing a 3x3 pile group against a 3-foot diameter drilled shaft. And we set off a series of small explosive charges, maybe 1 to 2 pounds, to liquefy a volume of soil. And then we used a high-speed hydraulic actuator to push the pile group against the drilled shaft. And we found that we could successfully liquefy soil and perform these tests without too much problems. And so we started to look at other than laterally loaded piles and liquefied soil. We started doing tests to evaluate negative skin friction in downdrag conditions. So the first one was in Vancouver, British Columbia, 32 centimeter, so a 1-foot diameter steel pipe pile. Went to Christchurch, New Zealand, and investigated 2-foot drilled auger cast piles. Went to Mirabello, Italy, working with INGV, an Italian research agency with I think 10-inch micro piles. Worked with Rick Kaufman at the University of Arkansas and Terrell, Arkansas, looking at large drilled shafts and 45 or 18-inch driven piles. And lastly, we've done some tests in back at Mirabello, Italy again, with tapered single piles and pile groups to see how that might affect results. So I'm going to give you, before I start, our take on a design procedure for pile downdrag assessment. And then the rest of the time, I'm going to try and indicate how things would, the evidence for what we're doing. So the first thing we need to do is estimate the settlement versus depth profile and assume a neutral plane location. So we could use any of a number of curves and equations that are out there to estimate the settlement versus depth. So if we have our pile here and we've got a zone that might liquefy, we estimate the settlement, knowing the factor of safety and the density of the soil. So we could plot this settlement versus depth. And then we have to make an assumption about the neutral plane. So we're just going to make a guess to start with. We'll probably have to change it, but then we just start out with a guess. Knowing that neutral plane location, we're going to compute negative skin friction above the neutral plane and positive skin friction below the neutral plane. And we're going to use 50% of the skin friction that we would have at the ultimate condition prior to liquefaction for the liquefied layers. And then we'll find from that the required tow resistance Q sub B. So here's our applied pile load. We'll develop negative skin friction above the neutral plane, positive skin friction below the neutral plane. And then at the bottom, we'll determine the tow resistance that we have to support. Now we have to, the next step is to determine the settlement at the toe of the pile. And we can get that by saying that the settlement of the pile at the neutral plane is equal to the settlement of the soil. We can subtract the elastic compression in the pile going down and get the settlement at the toe of the pile. We can add to the elastic strains to the top and get the settlement at the top of the pile as well. So we next need to use a QZ curve to determine if the mobilized QB for toe settlement is equal to the required QB. So we're going to take this toe settlement and come up to our QZ curve. And then we got to compare to see if we have compatibility. Is it consistent with the toe, the tip resistance that we're expecting? And then we'll likely have to revise the location of the neutral plane and repeat the process until we get convergence. So the first test we performed was in Vancouver, Canada, and it's reported by Rollins and Spencer. If you're a structural engineer, you might think a bridge would be a good idea here, but Massey Tunnel is located underneath the Fraser River at this location. And we got permission to do tests at this Canadian liquefaction experiment site. Soil profile at this site consists of fine sand and silty sand with some silt layers. Were not considered to be liquefiable. The relative density is typically about 40% in this zone. Based on frozen samples, the SPT, equivalent SPT was taken as 10 in the target zone, and the value was 17 near the toe of the pile down here, which was about 21 meters below the ground. Right. So our objective was to target this zone from about 5 meters to 13 meters to be liquefied with the explosives. So this is our test setup. We had a test pile with a reaction frame, 4 reaction piles to hold it in place. So here's our test pile in the middle, our 4 reaction piles holding the test frame in place. And then these are our 8 blast holes. We set off the explosives sequentially, as you see here. And we've got strain gauges along the length of the pile to measure the strain to get our force in the pile. And we've got pore pressure transducers to monitor the water pressure that develops. So the sensors, we had pore pressure sensors located at various depths throughout the profile. These can take the high transient blast pressures and not be damaged and give us reasonable accuracy, maybe 0.1 psi for the residual excess pore pressures. We also had Sondex settlement system to monitor settlement versus depth. This consists of corrugated pipes with metallic rings. With this probe, we can identify where the rings are to start with and then go in and see where they ended up afterwards. So this is a video of that blast test. And once it goes off, we've got hydraulic jacks here applying pressure to the pile. Once the blast goes off, you'll hear pumps start to go off to keep the applied pressure constant, because there's enough settlement to reduce the applied load substantially. I want you to look at this pipe that's sitting in the ground. It's just steel drill rods, and you'll see that settle as the soil liquefies. So when the explosives went off and the soil liquefied, you can see that drill rod settled about a foot. The settlement at the time of the blast caused a decrease in the force in the pile, about 160 kilonewtons or 36 kips. So we tried as quickly as we could to get back up here to the initial applied load. Our applied load was about 50% of the ultimate capacity of the pile. So we had a factor of safety of about 2. And we had to continually add load to keep that load relatively constant. The excess pore pressures, as you can see in this figure, are with each blast detonation are gradually increasing, and we get up to near 100% RU value of 1 for values from about 6.4 meters to 12.8 meters. And this one down here is near the toe of the pile and didn't get values any higher than about 0.1. After the blast detonation, the excess pore pressure started to dissipate with time. It took about, I think 17 minutes for the excess pore pressures to dissipate back down to less than an RU of 0.1. The pore pressures dissipated from the bottom up. The top pore pressure sensor had the highest pore pressures throughout the dissipation process, or excess pore pressure, I should say. So let's take a look at the settlement trough that developed around the pile. You can see that this is before the blast, 2 minutes after the blast, and 10 minutes after the blast. So you can see we're causing settlement to take place in a large section of the profile. The charge holes were located about 5 meters from the test pile in the center, and the soil around that settled about 11 inches near the pile, and that settlement trophic or dish, whatever you'd like to call it, extended back to about 13 meters from the test pile. This is the test pile before liquefaction, and this is the test pile after liquefaction. We had about, again, 27 centimeters, 11 inches of settlement. And if we look at that over the zone that liquefied, we have about 3% volumetric strain. it's a weird experience to go see this. Your mind is so used to the soil staying stable that it looks like the pile is floating up out of the ground, but it's that the soil is settling right before your eyes. This plot shows the settlement versus depth from the Sondex device. We think there's some slippage that takes place here, so we've extrapolated this out. And from the Sondex, we're measuring about the same amount as we're getting from the ground surface surveys. So a fairly linear settlement versus depth profile here with a maximum settlement of 11 inches. So it's interesting for us to see how that compares with the liquefaction settlement that we might expect from an earthquake. So we took a value, if we take a value for the SPT of 10, and we know that it liquefied, so we're above this boundary here, we would expect a volumetric strain of maybe 2.5% with the Tokimatsu and seed approach. If we look at Yoshimine and Ishihara, we know it liquefied again, and if we use the value for an N of 10, relative density of 50% here, and use the limiting value, we're at about 3.5%. So the 3% volumetric strain that we're seeing in the test is right in the range of what we'd expect if liquefaction were induced by an earthquake. This plot shows the load in the pile. The blue curve shows the load in the pile just before blasting. So we've fully mobilized the resistance from side resistance in the test or in the initial loading. We're going to look at this section right in here in the liquefied zone. Just after blasting, the load in the pile is close to vertical. It's not completely that way, but close enough for practical purposes, indicating that soil has liquefied and we've lost our friction capacity or positive friction capacity in that zone. At the end of settlement, we get a negative friction or increase in load in the pile. If you compare above that liquefied zone, things are not quite what we would have expected. We would have expected this to start here and go negative from the top. But when we started to reload the pile after the blast went off, the reloading produces positive friction from the top downward. And that gives us a downward force from the ground surface to 6 meters of about 160 kilonewtons or 36 kips, which is exactly what our resistance was in this zone. If we look at the positive ultimate skin friction before the blast, it's about 180 kilonewtons in that liquefied zone. After liquefaction, the average resistance is about 90 kilonewtons. So our average resistance in the liquefied soil from negative skin friction is about half of the resistance that we'd expect to occur. Now, we're going to look here at what happens when you reload a pile following downdrag and use a case history from Scandinavia, reported by Mike Bozazuk in an article in 1981. So in this soil profile, they just drove the pile and let it sit for 10 years. So this is a fabulous opportunity to learn from this experiment. And after that, they loaded the pile up. And as they loaded the pile from the top down, you can see that the negative friction is decreasing and becoming positive, and eventually experience a plunging failure. So it's not unusual to see a positive skin friction develop from the top downward when we reload after liquefaction. Now, what happened at the end of the process, if you look at this curve that shows the settlement, or shows the excess pore pressure dissipation with time, this curve shows the ground settlement and pile settlement with time. And this shows the applied load versus time. So as the excess pore pressures decreased, both the soil and the pile settle. As the pile settles, the applied load drops, and the pump has to be used to add fluid to maintain the load as we go throughout this process. And after 30 minutes, as we approach the end of the settlement of the ground stays relatively constant, but the incremental pile settlement exceeds the soil settlement enough to maintain a negative skin friction that we see at the end of the test. So can we look at the overall behavior and see how we would deal with this? So this is the same plot I've shown you previously. We played around and this looks like our neutral plane. We've measured the strain, the load in the pile, and the strain has been measured. So we can plot the settlement versus depth in the pile. We have the settlement of the soil versus depth. And so this is our neutral plane where the settlement of the pile and settlement of the soil are the same. With this, we have to extrapolate because we have some failures of the strain gauges at depth. But it looks like from our measured QZ curve here that we need about 100 kilonewtons, or about 25 kips at the bottom. And then things are in equilibrium. So not very much movement is required to develop that, the required end-bearing resistance in this case. Now, what would have happened if we had had a constant applied load? Now, instead of having reapplied the load here, we'd have settlement causing an increase in the load due to drag load, which would increase down to the neutral plane, and then it would decrease with depth to the toe resistance and define that value. Playing around by trial and error to get the neutral plane, it turns out to be at this point midway through the liquefied layer, and we'd expect 100 millimeters of settlement, maybe 4 inches here, to see if we would be consistent with the amount of toe resistance we need for that neutral plane location. We can plot this against toe of our QZ curve, and you'll see that we can develop the 400 kilonewtons of resistance at 100 millimeters or 4 inches of settlement. Now, from a conceptual view, under static loading before liquefaction, we could estimate our side resistance as K times the tangent of the interface friction times the vertical effective stress times the area of the side. Or we could use a beta value times the initial vertical effective stress times the area of the side, using the static water pressure for the effective stress. Immediately after liquefaction, the excess pore pressures have increased to the vertical effective stress, and our side resistance goes down to a very low value, or 0, which is what we saw in the test. So our beta value would be 0 relative to the initial vertical effective stress. Now, during reconsolidation, the pore pressure is decreasing to 0 and the effective stress is increasing. So our negative or downward friction is increasing. And from this test, we found out that beta during reconsolidation at the end of the test was 50% of the beta that we had for ultimate positive skin friction before liquefaction. Now, one question that remains unanswered from this test in Vancouver is what happens long term? Does our side resistance regain its strength after liquefaction, or do we have a permanent loss in strength? And we'll look at that a little later here now. The next opportunity we had to do, well, let me go back and just say that one test is not enough to build a design procedure on. But we didn't have a lot of opportunities to do another test until the Christchurch earthquake sequence in 2010 to 2013, which caused tremendous damage in New Zealand, $40 billion worth of New Zealand dollars worth of economic impact. And 33% of that loss was due to liquefaction-induced damage. Our colleagues in New Zealand invited us to help with the blast liquefaction test program, and they gave us a site where we could do a downdrag test. The soil profile at this in Christchurch, where we did these tests, site 4 consists of sandy silt to 2 meters, where the water table typically was located. And we had some clean dense sand and some dense to medium dense sand below that. We have Q sub C values of about 12 megapascals, shear wave velocity less than 200, indicating it could be liquefiable, and a relative density of 60%. Now, this is the case after this had been subjected to multiple earthquakes and aftershocks, so that the relative density before this these tests that we did is probably lower than this. So we had a contractor in New Zealand install auger cast piles designed to be 0.6 meters or 2 feet in diameter. We put one into 8.5 meters, another to 12 meters, and another to 14 meters, so that we could see how things would vary with piles that went through the liquefied zone in contrast to piles that were embedded in the liquefied zone. And this is our estimate of where we might see the liquefied zone. We had 2 opportunities to do this. One where the piles were not loaded, so they're just sitting in the ground. We set off the explosive charges and liquefied the soil around it. And then we did another test where we have 270 tons of load produced by these crane mats and sorted weights that's acting on the pile. So we applied those after the first test, helped us get some idea of load deflection behavior of the soil, and did a subsequent test. We had instrumentation to give us the strain gauges with sister bars and thermal integrity sensors to give us a better estimate of the diameter. And that turned out to be really useful to have this information, because the piles turned out to really be 0.7 to 0.75 meters in diameter, not 0.6 as designed. So this instrumentation was very helpful. So let's look at what happened for the test with no load on the piles. Here's the blast going off. You'll see about 335 pounds of explosive being detonated in 10 seconds. So my wife asked if they actually pay me to do this, and I say, yeah, they really do. Our test piles were over in this area. These other areas were different ground improvement strategies compared to an untreated area. As soon as those went off, we could see pore pressures being developed that brought sand to the surface and created the typical sand volcano or sand boil that you'd expect to see. So this went on for 15 or 20 minutes, and we got some fairly large sand boils developing. So this is me kneeling in front of one of the sand boils. You can see it's pretty large. This shows the sand boils that developed around our test piles. So we're plotting here in this diagram the excess pore pressure versus depth. This is the effective vertical stress in the profile. And we developed excess pore pressures that were high enough to equal the vertical effective stress prior to blasting. So we'd liquefied down to maybe 13 meters. So from laser scan from Michelson at Oregon State, we found that the ground was settling more than the piles at the surface. And I'm showing here plots of the load in the pile versus depth for the 8.5 meter pile, the 12 meter pile, and the 14 meter pile. The colored lines are the cases or what was measured. You can see that there's a neutral plane in each case. It goes a little deeper for the deeper piles. There's negative friction above, positive friction below. Now this dashed line is our best average of the percentage of the static resistance that we needed to have, or the percentage of the positive ultimate resistance we needed to get agreement with what was measured. Over here, I think this must be an offset in the strain gauge from the blasting, but I think you can see the trends that are taking place here. Now, overall, the negative friction in the liquefied sand layers at the end of consolidation was between 43 and 55% of the positive ultimate friction before liquefaction. So now this is giving us a little more confidence that the value from Vancouver, Canada might be a realistic thing. We're plotting here the settlement that was measured at the neutral plane in comparison with the range of soil settlements that were measured. And we're not too far off of the values that were expected there for the neutral plane assumption. Then again, we applied these loads to the pile so that we eliminated the negative friction that had been developed from the first blast test, and used this loading to get load versus deflection curves to give us capacity of the pile. I started to get pretty worried the night before this test that this whole thing was going to tip over. So I tried to shift the weights around so that we had more of the weight on this back piles here and less on this front pile that was settled, that was going to be in the liquefied zone, to try and keep things in equilibrium. We measured, we had a steel frame to support the weights and test piles to carry the weight of all those 270 or 300 tons, English tons. And then at each, over each pile, we had a load cell that told us what load was being carried by each of the piles throughout the test program. So this is a video of the test blast going off. I've got a line in here for you to see how the settlement is taking place with time. So you can see that a large amount of the settlement occurred when the friction went to zero in the liquefied zone, but some additional settlement still took place afterwards as the pile reconsolidated. You can see that there's a tilt here, And you can see also the sand boils that developed all around the test piles. In this case, the load on the piles was large enough that we had, and we didn't quite use enough explosives, I suppose, maybe, but we've got liquefaction or close to liquefied state from about 3 meters down to 8 to 9 meters. And nevertheless, the settlement of the loaded piles was more than the settlement of the surrounding ground. And as a result, we have positive friction all the way down, even through these liquefied layers. We lost some lead wires in the 8-meter pile, but we have results from the 12-meter and the 24-meter pile. The colored lines again are the load measured in the piles for the test. Here's the liquefied zone. Within the liquefied zone, the dashed line is 42% of the pre-blast positive ultimate skin friction. And in the non-liquefied zone, we're getting 100% of the pre-blast positive skin friction. So once again, we're seeing values that are somewhere between 40 and 50% for that set of 5 tests. We had an opportunity to go to Mirabello, Italy, in northern Italy near Bologna. If you'd had that chance, you ought to take it. This had been subjected to an earthquake in 2012, and there were fissures with each sand ejecta and sand boils throughout the area. So we knew this was an area of liquefaction. Liquefaction ejecta came to the surface even though there was 6 meters of silty clay to clay silt of the soil profile. We set off 2 decks of explosive charges in sequence, like I showed previously. Here's our micropile. We monitored the settlement with Sondex tubes, and we monitored the excess pore pressure that developed in the strain in the piles. This is the cross section. There's a steel pipe that serves as the reinforcement. It's 10 millimeter wall thickness, and we have these strain gauges around with on either side and cement grout. We exhumed them afterwards to see that we were getting what we thought, and it looked like it was about what we'd planned. We didn't have the money to do a static test, but we did do drop tests to evaluate the static pile capacity. We did these tests before blasting, and then we came back and did the test after blasting so that we could use these results to get the full load versus deflection curve for the piles and the end bearing or the toe resistance. So here's the blast going off in this case. And we saw liquefaction occurring very soon after the blast, ejecta coming through the blast holes. So the red or orange curve here is showing the load in the pile based on the CAPWAP analysis, and the blue is the average resistance in the, after the blast. So this is the zone that was liquefied. Our neutral plane sits up here a little higher. That's where the ground surface or the ground settlement was equal to this settlement of the pile. Then we have positive friction below, going down to a value of 187 kilonewtons at the tip. By taking the value of settlement of the neutral plane and subtracting out the elastic compression, we get a settlement of 13.7 millimeters. And adding it in this part, we get 15 millimeters of settlement, which is consistent with what we're measuring. This shows the toe settlement versus toe resistance, or QZ curve, obtained from CapWAP. These are the 2 tests before blasting, and these are 3 after blasting, where we had larger settlements that had already taken place at the toe. And they're fairly consistent with the Reese-O'Neill QZ curve that's shown here. Now, from our blast test with a settlement of the toe of 13.7 millimeters, we were expecting something like 195 kilonewtons, which is close to what was observed. How did this compare with what we would have expected from the pre-blast ultimate skin friction? In the non-liquefied zone, we're seeing about 82% of the positive skin friction. And in the liquefied zone here, we're getting about 46% of the ultimate positive resistance. Below that liquefied zone, the pre and post blast side resistance are about the same. I'll just show one last single pile test. And this is for a tapered pile that was also at the Mirabello test site. And we were wondering if you had a cylindrical pile, the soil would settle along the side of the pile. But if it's tapered, and I've exaggerated it here, if it's tapered a pile, the clay might tend to settle away from the pile and reduce the negative skin friction. We wanted to see if that would be true. In the liquefied soil, we thought maybe this is a potential way to mitigate the hazard of downdrag or negative skin friction, drag load, because the soil might settle away from the pile. But it could also flow into and come back into the pile. So we're looking at that possibility. When we look at liquefaction induced in pile groups, we sometimes think that this will be all a uniform settlement down to the neutral plane with negative skin friction. But limited tests show that there might be greater settlement and drag load at the edges than on the interior of the pile. And Jean-Louis Briot and Tucker in 1997, their NCHRP report found that in clays, the drag load or the negative friction on the piles inside the group was about 20% of that on piles at the edge. So Geo-Fondazione, a pile driving contractor, donated all the piles and the cost for the tests. We donated our time to come do the test with them. Here's the setup. We have 3 single piles with reaction piles for each of those piles so that we can do tests after the blast. We have a group of 13 piles here that can help us understand a little bit about the behavior. And we have 8 blast charges located around the perimeter of a 7-meter ring. Again, we're monitoring with excess pore pressure with pore pressure transducers. We have profilometers in place here and here to see what might happen. Here are the tapered piles being driven into place by Geo-Fondazione. So they're 51 centimeters at the head and 26 centimeters, about a foot at the bottom. There were 16 hollow tapered piles that we drove, and 7 of these were instrumented with strain gauges at about 1.5 meter intervals. Prior to doing any blasting, Geo-Fondazione set up a reaction frame so that we could do a pile load test. I'm at a pile 20 just outside the area of the blast holes. This shows the load versus settlement that we're seeing for that test. Here's the test being performed. And more importantly than just the load versus deflection of the pile, we wanted to know the load versus deflection or load versus depth in the pile. In this case, we're getting side resistance is producing about 80% of the resistance because of primarily that tapered pile. And the toe resistance is producing about 20% of the resistance here. So we're getting out to a value of 2,700 kilonewtons at ultimate state. This is as large a load. We probably could have done a little more if we'd had a bigger frame, but we're maxing out our capacity. We used the data we got from the test to come up with a QZ curve based on our load in the pile versus depth information. Prior to the blast, we applied a load that was about half of the pile capacity, ultimate pile capacity, and then set off the explosives. Again, this is that profile. It's a little bit different at this site, some clay and some sandy silt, maybe to 4 transitions from 4 to 4.5 meters. Then we have this liquefied silty sand and silty sand below it that was not liquefied. So this is a plot of the reload in the pile. Again, it was very similar to the load versus deflection or load versus depth curve that we had from the first pile test, developing very little end toe resistance. This is to remind you is the ultimate resistance shown in green. After the blast, immediately after the blast, we had some increase in load in the pile. And then within the liquefied zone, or where the pore pressures were relatively high, 70 to 100%, we saw this nearly vertical load versus depth curve indicating that the soil had really liquefied. Now, not to repeat our problem that we had in Vancouver, we told the contractor to just let everything come to equilibrium rather than try to maintain that load here. So at the end of the settlement process, the load at the top of the pile was 600 kilonewtons, and it then we had negative friction. Negative friction developing from the ground surface down to about 10.5 meters. And then positive friction developing below to keep the pile in equilibrium. So if we look just at the ultimate resistance, or the resistance after the end of blasting and settlement, you'll see the applied load of 600 kilonewtons. Here's our neutral plane. This is the negative friction acting downward on the pile above the neutral plane, and positive friction acting upward below the neutral plane. If we compare the friction, we're getting 80% of the ultimate positive friction in this clay layer. This could be due to the pile settling away from the soil to some degree. In the liquefied zone, we were measuring an average of 60% of the ultimate positive friction. And below, we're very close to the ultimate positive friction in all that zone below it. So looking at negative friction for the tapered piles, it looks like maybe we could have had a 20% reduction of side friction relative to the cylindrical piles. It could explain what we measured. But the piles in the liquefied sand, they're still giving us a value that's very close to what we measured for the cylindrical piles. So it doesn't appear that the tapered pile is having any beneficial effect for the liquefied sand. The soil just flows into the pile surface itself. So it's about the same reduction in side friction for negative friction as what we saw for the cylindrical piles. Here I'm showing a settlement of the excess pore pressure for the pile group and single piles. There's a little zone here where we don't quite get things liquefied. That might explain the higher than normal load transfer in the pile in this zone. Here again is the zone of liquefaction or high pore pressure zone. And here I'm plotting the settlement of the soil and the settlement of the pile that were measured. So this is our neutral plane, which looks about right. And the settlement, let's see, if we extrapolate, this is our neutral plane. If we extrapolate we've got negative friction above the neutral plane, positive friction below, like we've seen before. If we extrapolate downward, we would expect load in the pile of about 400 kilonewtons. Got some wiggle room in that, of course. If we extrapolate to the bottom of the pile here, we would have a settlement of about 0.4 centimeters. So how does that compare with what we would get from our QZ curve for 0.4 centimeters or 0.4 millimeters? We're getting about 430, something like that, very similar to what we were needing to have equilibrium. We did two other tests, and we're getting very similar results. So this appears to be the negative friction it's not a one-off, it's consistent. So summarizing for the single pile test results for these 5 different test sites, I didn't have time to talk about Arkansas, but we're seeing values between where the negative side friction in the liquefied zone is between 40 to 60%. So we think a value of 50%, which I indicated earlier when we're talking about the method, might be an appropriate value. Some conclusions based on the single pile testing. In the non-liquefied soils, the negative friction was equal to the positive friction, the positive ultimate friction for cylindrical piles, and for this one test that we have available, 80% for the tapered piles. In the liquefied soils, the negative and positive skin friction after liquefaction and reconsolidation were between 43 and 60% of the ultimate skin friction before liquefaction. So we suggest a value of 50% for design. These values are consistent, generally consistent for the available test results we have now, which are 17 piles and different pile types. And this suggests that this might be a typical result. The depth to the neutral plane increased and pile settlement decreased as the pile length increased, which is consistent with the neutral plane approach. Pile head settlement was also generally consistent with the neutral plane concept. We found that reloading develops positive friction from the top down, and that several months might be required for the liquefied sand to recover its full side resistance. It looks like my time is basically spent, so I think I'll stop right there and entertain any questions that people might have. And
great. Thank you so much, Kyle. That was excellent. I do think we do have a few minutes for questions, and I'll go ahead and put a couple out there as we're getting started. But I'm curious about the locating the neutral plane. So you said that this is a trial and error function, but it must also be a function of the thickness of the liquefiable soil zone as well, too. So could you give us some insight into how you come in and work through that process of locating it?
Well, from our test, of course, we're measuring where the settlement is the same as for the soil in the piles, and we're measuring where the load changes from negative to positive. So we know where that value is, but for a designer, you don't know that in advance. So we typically would start near the bottom of the liquefied zone, and because that is where the settlement is the lowest, that usually produces a pilehead settlement that's much lower than the settlement of the surrounding ground. So for at our site in Vancouver, Canada, the settlement of the ground was 11 inches, but the settlement of the pile was less than 1/4 of an inch. So just because the soil liquefies and negative friction develop doesn't mean that you have a failure or a problem. You have to look at the settlement that takes place. So if things don't work out, then I just progressively increase the height of the neutral plane until I get convergence. It usually takes 2 or 3 stabs at it, and then you can converge.
Okay, excellent. We have a couple of questions from the audience. So one person is asking if you could give some insight into liquefaction impacts on shallow foundations.
That's a little outside my skill level, but it was part of my PhD research. So we found out that when you liquefy, when you have ground shaking, these more from numerical models, that the soil, at least for mat foundations, shallow mat foundations, the excess pore pressure ratio can be significantly lower than the excess pore pressure in the free field. And that can lead to a case in some situations where the settlement could be less. But if you're considering shallow spread foundations, the liquefaction usually leads to excessive settlement taking place because the excess pore pressure outside of the soil underneath the footings can flow inward and essentially liquefy the soil afterwards because the pressures are higher on the outside. So it's been pretty much standard practice to try and use deep foundations to avoid that kind of problem that could occur. You can use some of the new methods that are coming out that from John Bray and Shida Dashti that give you ability to predict settlements due to both volumetric strain and shear strain effects. And there may be conditions that you could find where the settlement would be acceptable and you could use a spread footing or a shallow mat foundation and still have acceptable performance.
Good, thank you. We have a couple of questions about the test protocol. One is, I sense that the close proximity of the blast introduced higher amplitude into the setup, hence influencing amplification of the ground. I'm sure the proximity factor should be accounted for. Did you have comments on that one?
Yeah, we're not necessarily trying to replicate an earthquake condition. We're trying to induce excess pore pressures that might be typical of an earthquake, and we're also trying to produce settlements that might be similar to what you might see in an earthquake. So we're not trying to replicate the ground motions or vibrations that would take place. We are producing shear strains that would be large enough to generate excess pore pressures. I hope that helps. Yeah, there's sometimes some confusion on that. One thing you can do to try and get an idea of this is to back calculate what acceleration level would be required to produce that same thickness of liquefied soil for a magnitude 7.5 earthquake, and maybe give you some idea of what the stress levels are that you're producing. But that's in its beginning states. So there's some work that is being done at Oregon State to look at shear strain and try and correlate that with excess pore pressure that's being developed. But this is more than what we've tried to do.
Yeah, excellent. We had some questions about the reaction piles that you used as well, asking if there was anything unique or different about those, because all of the piles seem to be within the influence zone of the blasting, and so they would have also experienced liquefaction as well. Is that accurate?
Yeah, we tried to have the reaction piles far enough away that that they wouldn't affect the loading, but we didn't try to completely remove them from the liquefied zone. So there could be some uplift that takes place. We didn't see, we monitored the settlement of some of the piles, particularly in our site in Mirabel, Italy, and we didn't see any significant uplift that was taking place when the soil's liquefied. So they must have had enough capacity to resist that problem. It doesn't really matter for us to find out what's going on, because we are monitoring everything independently of what is happening to the reaction frame. So we're monitoring the load in the pile, we're monitoring the excess pore pressure, we're monitoring the settlement. And so it's not that critical for us to what the reaction piles do, as long as they hold things in place.
Fully instrumented, right?
Yeah.
So I understand these are massive field scale tests, which are difficult to coordinate and a lot of work, it's remarkable, the series of tests that you've put together. We have one question asking if you have had the opportunity to look at the effect of pile spacing on the settlement.
Well, I have some slides to show you about pile groups. And when we put pile groups together, we get quite a bit different behavior there. On the interior piles, we get less settlement than occurs out in the free face away from the piles. And we dramatically decrease the downdrag, or the drag load, I should say, in the non-liquefied soil in this clay layer above the liquefied layer. One other benefit of having closely spaced piles in a group is that we clearly saw substantial increases in cone resistance on the order of 30 to 50%, and increases in lateral earth pressure coefficient that were measured with a combination of the dilatometer and the cone penetrometer. So those two things give you a beneficial effect that gives you more resistance to liquefaction around a group of piles than you would have from an isolated single pile.
Excellent. One person in the audience noted that some of your tests were done in relatively close proximity to nearby structures. Did you do any observation, or were those abandoned structures?
When we tested at Treasure Island, there were buildings immediately across the street from us. So I would guess maybe 200 feet away. and there wasn't any damage to windows or any cracking to the structure. The Navy let us use that site on Treasure Island, and but we didn't have any damage to speak of that gave them any concern. The only problem that they had was that we caused some vibrations down to a filming studio, and they said we can never do that while the TV show is being filmed. That's our high priority. So we tried to work around the filming of the Nash Bridges show that was being filmed down there.
To get the production schedule before you started.
That's right. Said, no, better stop.
Okay, good. So here's another one from Chris Hunt. Do you think that there was a time during liquefaction when the skin friction would have been less than, for example, the average 50% of the static resistance, and then it recovered? Do we have any cases where skin friction would have been less than the average 50%?
What normally happens when we have a load on there is that it decreases from the positive condition back to the negative condition. So there's a time in between there where it could be zero. Yeah, and it does happen. It could be in the liquefied zone, it will start out at zero and then it increases. We're looking at in our test at the end of settlement, and the averages that I'm showing are for the end of consolidation settlement, but there can clearly be cases in between that go from 0 to 50 or 60%. Yeah. We were looking for a more critical case, which would be the higher values.
Yeah, yeah. And then we have a couple of just housekeeping questions here. For the profile shown for pile 20,
yes,
versus the QZ curve, I think the units show 0.4 centimeters versus the QZ curve with 0.4 millimeters. So it looks like maybe that's a typo. Is it centimeters or millimeters?
I think it's millimeters. I know it's millimeters. Yeah, it's very small.
Okay, beautiful. And then one of our audience members asks where they can find references for your published papers on these topics.
That's a good question. We've published a number of these in conferences and I think Springer has a publication that's let's see if I can find it. Developments in Earthquake Geotechnics, the title, and it shows we show results from the Treasure Island case and the tests in New Zealand. There's tests in, it might be better if I put out I should have put out a listing that shows the references. That might be more helpful to you.
Yeah, it's great. I'd put them on your website.
In a series of conferences mostly, but we're trying to get those published in journals at the present time.
Okay. Do you have them? There should be a list on your faculty website. Is that right?
Yeah, they'll be there for sure.
Okay, perfect. Good. Well, thank you so much, Kyle. That was excellent and very, very enjoyable. So I'll turn everything back over to Brad now.
And there's not much more to say. That was a fantastic presentation. And thanks, Susan, for moderating. Of course, thanks to all our viewers, especially those who asked questions today. It's always more fun when things are interactive, so we really appreciate it. And if you liked what you saw, and I always say, you're here at the end, so you probably did. Click like, subscribe, get notifications. We'll let you know every single time we post something to the YouTube channel. We will have one more Cross USA lecture with Kyle, a live streamed version, and that will be the first week of September. You can register for that on our Eventbrite page, along with all of our other live streams. And our next live stream will be August 1st. We're starting a brand new series on GI publications. And the subject of the first episode will be a brand new manual of practice on geoenvironmental, engineering that just came out from our Geoenvironmental Engineering Committee. Our guest will be Dimitrios Zekos, so you'll want to be there on August 1st for that. You can get more information on that on our Eventbrite page as well. So Kyle, thank you for doing this. I hope it's been a fun year to do all these lectures, and you're getting down really to the end, but you've reached so many people with them. It's such a cool thing. We really appreciate you continuing to do this.
You're welcome. It's been a pleasure. It's been a pleasure.
And so for everybody out there, we will see you again very soon on another GI live stream.